have Avik Banerjee from the Eurostrings.
Okay, so thanks to the organizers and apology to the attendants for coming in between you and your nap after a nice lunch. This talk is based on a recent work with Giuseppe Policastro and Nambu-Goto, and it's accepted for publication in JHEP. And what I'm going to talk about is primarily about ADS3 CFT2, and I also comment on its generalization to higher dimensions. So in bottom-up holography, we are all familiar to this thin-brain model of interface CFT2, right? So we have two CFTs glued across an interface or defect. For example, this can be a junction of a quantum wire, and in this model, and this model is like you glue two locally ADS3 spacetimes across a tensile string. And this model has played a significant role in, for example, computing the transparency properties of this interface or to find the phases of this interface. But in this talk, I'll be asking a broad question, which is as follows: that we know that in holography, the gravitational dynamics emerges from the stress tensor dynamics of CFT. So the question that we want to ask is like, can the dynamics of this string somehow emerge from the dynamics of this interface? That's the broad question. Now, in our first work, we only have glimpses of this answer, but I'll tell you I'll only present you the glimpses of this answer, but I'll more completely answer a slightly less ambitious question: is that can these Nambu-Goto dynamics emerge from gravitational dynamics? Why do I ask the second question? Because we know that if you have a point particle in a curved space-time, and it's the Bianchi identity restricts the particle to move along geodesic, which extremizes its path, right? We know that Nambu-Goto equation extremizes the world sheet. So can Nambu-Goto equation also follow from gravity? So that's the question that I will answer more concretely and also give you something to the answer of this question. Now, since there is a shortage of time, let me first advertise the answer. So the answer is as follows. So the solution of gravitational equation, junction equations of gluing to local ADS3 is also true for locally flat, but we will not talk about flat spacetimes. So if you have two locally ADS3 spacetimes and you glue them according to some junction condition, I will tell later. And then the solution has essentially three parts. The first part is, it's like as if this string is a probe string in a continuous background where it satisfies a Nambu-Goto equation. That's one part. The second part is the correction due to tension, because we are considering a tensile string. And the third part is slightly new. It's something we call rigid deformation, which is related to the isometries of the wall sheet or the isometries of the embedding spacetime, which shifts the wall sheet. I'll talk in more details about this later. Okay? And since this is a perturbative construction at higher orders, it will essentially be you'll see the cross term between these three modes, but these are the essential building blocks of these solutions. The question is, why is the emergence of Nambu-Goto non-trivial in this context? You see, the kind of action that we'll consider here is of this sort. So M is like it's a two copy manifolds. This has these two conformal boundary and this wall sheet boundary, and where we have this given circuit term. If you think that this is a perturbative construction, so you can send the tension of the string to 0, so it's like a probe string, you can see that if you set the tension of the string to 0, you get nothing. More non-trivial reason is as follows: that Nambu-Goto equation follows from Nambu-Goto action when you vary this part of the action with respect to the embedding coordinates. What I will show you is that Nambu-Goto equation will follow from the variation of the metric. The metric is the only dynamical field here, not the embedding coordinates. So this is where the non-triviality lies in the setup. Okay. So what is the setup? Let's get into more detail. So we have, let's say, two copies of the same geometry. It's very important in this part. So here we have considered doing two same geometries, and for simplicity, we'll just take them to be a BTZ black hole of mass m, both of them. And these two strings essentially divides both of them into two halves. You can glue any half with the other. So for example, here we'll glue the left one of M1 with the right one of M2. So there are two world sheets, so we have to fix the gauge redundancies, which we do as follows. So first we'll fix the gauge redundancies of this world sheet by choosing this tau r, sigma r to tau l sigma, and essentially we call both of them as tau and sigma. It's like we are identifying the two world sheets, but I still have two gauge redundancies, which I fix as follows. So this is like my fixing the all gauge redundancies of this two world sheets. So I will. Now, subject to this gauge, the most general solution, the most general embedding that you can think of is of this form. And these tau a, sigma a, FL and FR are essentially as degrees of freedom. Okay. But in what follows, we essentially consider a symmetrized and antisymmetrized version of FL and FR because they naturally decouples in these gluing equations, which are as follows. So these are standard in general relativity. So you claim the continuity of the induced metric across the world sheet, and you also claim that the Brownian stress tensor, the discontinuity of the Brownian stress tensor is due to the stress tensor on the world sheet. And here we are just considering a tensile string. So the world sheet stress tensor is simply the tension times induced metric. So here we have initially we have 3 plus 3 6 equations. But we also have this Hamiltonian constraint which says that Brownian stress tensor on either side must be conserved. So that reduces 2 equations. So essentially we have 4 equations. And this 4 equation essentially solve for these 4 functions. So now you can see the decoupling of this degrees of freedom. Okay. Now you may wonder that can we generalize this strategy to higher dimensions? It turns out it does not. If you do this degrees of freedom counting, for example, when you are going to d-dimensional space-time, you have 2D embedding coordinates, and you have this many number of world sheet reparameterization freedom. So when you subtract them, these are the number of embedding coordinates that you have. Again, these are the number of conditions that follow from the Israel gluing, and you have to take into account this Hamiltonian constraint. So you have to substitute this from the sum of these two. So these are the number of equations that we have, and they only match at d equal to 3. So d equal to 3 in some sense is special in this context, but I'll comment on its generalization to higher dimension later. So let's stick back to d equal to 3. So essentially we have these equations, and these are the degrees of freedom that we want to solve for. Now when we consider static fluctuations, then one can solve this equation exactly. This has been done before. But for dynamical fluctuations, you cannot solve this equation exactly. So what we do a perturbative expansion of these functions, and what's next? Yeah. So here epsilon is kind of a
generic metric on the two sides. You cannot solve it exactly, or I mean there are cases where you can solve it exactly, right?
if it's a static, if the perturbations are static, then you can solve.
Well, no, also if it's not static, also if it's a wave moving towards the string, you can solve it.
For arbitrary BTZ geometries,
Well, no.
arbitrary one-other spacetimes.
Vacuum
No, I'm talking about one-other. And here is epsilon is a bookkeeping parameter. So, and I will suitably modify this tension with epsilon times T naught to make this equation consistent with this perturbations. So earlier, these perturbations were solved up to linear order, imposing Dirichlet boundary condition on all these 4 functions. Okay, this is the work by Polycastro. Shira was a co-author in the computation of holographic transmittance and reflection coefficients. What we'll do, we'll essentially solve this equation very high up. We did it for up to epsilon to 8th order, and we'll impose a less restrictive boundary condition, which is as follows, which will relax Dirichlet from this tau a, sigma a, and xa. We'll only impose Dirichlet on this xs. I'll tell you the reason why of this. You can actually, in principle, relax it from xs, but that does not help our purpose to show the correspondence between Nambu-Goto and this gravity equation. So this is the minimal we do. We put Dirichlet on this xs, while we keep these 3. We impose nothing on them so far. Okay. And in a parallel exercise, we'll solve for the Nambu-Goto equation of a probe string in BTZ black hole of mass m, with precisely this Dirichlet boundary condition. That's why we essentially, just to compare, we impose this boundary condition on this XS, but otherwise we leave the other modes free. Okay. So what happens? Okay, and here, okay, so here we are considering the fluctuation around a straight string, which is an exact solution in this setup. So let me show you the results in some order. So at 0th order, this is obviously satisfied because the straight string is an exact solution of this gluing problem. At first order, we get the solution something like this. We do not see the symmetric part here. It appears in the next order. So here we see three parameters, alpha h, beta h, and gamma h, and these are nothing but the generators of SL2 of the SL2 isometries of the ADS2 world sheet. Okay. These are the generators of the SL2 generators of the ADS2 world sheet, which is the world sheet is ADS2 at first order. When you start perturbing, sorry.
My God, you have 10 minutes.
Oh, thanks. Yeah, so we start from the straight string, the lead at first order, the world sheet is ADS2, and these are essentially generators of this SL2. Whereas the extrinsic, so H is the continuity of induced metric and K is the discontinuity equation. So this is the solution that you get you get the solution for XA1, which is of this form. And here again you see three similar parameters, and these are related to the isometries of the BTZ black hole spacetime, which shifts the world sheet, preserving its extrinsic curvature. Okay. Now you can say that these are isometries, so you can always gauge it away, but you better not gauge it away, because if you go to the boundary of the world sheet at sigma equal to infinity, you see that these are large diffeomorphisms. They do not vanish. Earlier they vanished because of this imposing Dirichlet on all the modes. You don't see them. So here we will not apparently not do that. However, our spacetime has another boundary which is at the horizon. And if you impose an ingoing boundary condition at the horizon, that kills out of this this exponentially growing modes beta h and beta k. Okay. So you're still left with 4. If you wish, you can still kill the alpha k and beta k from this XA1. This is what we call the rigid deformation parameters, and this, if you wish, you can kill this alpha k and gamma k by imposing a Dirichlet on XA1, so that similar to XS. But we'll keep this at least this alpha h and gamma h for two reasons, which are as follows. The first reason is that, especially if you look at this gamma h, alpha h is a constant. If you compute the Schwarzian of this time reparametrization at the boundary, this is given by this. M is the mass of the BTZ black hole. So it's like if you start with a conformal interface which do not have a stress tensor, what this reparametrization is doing, this inducing a stress tensor on the world sheet, and this reparametrization mode this is making, so you can essentially now talk of a dynamics on this interface, you can try to write down an effective theory for this tau is these reparametrization modes. That's reason 1. The reason 2 is as follows. So I have been talking about the emergence of Nambu-Goto, but so far I have seen only, for example, a tensile correction and the correction for this rigid deformation parameter. So where is Nambu-Goto? So now let's go to higher order. I will show the all order result in the single slide. So at higher orders, the equation essentially gets complicated. So it becomes a three coupled, so I'm talking about the continuity of the metric. So this becomes a coupled differential equation of these three functions, sigma a, tau a with n index, and xsn minus 1. How do you solve it? So the way to solve it is as follows. So you first solve this sigma and this tau and express them in terms of this xs. These are some sources that comes from lower orders. And you essentially put the sigma a and tau a in this third equation. The non-trivial, then you have to take certain data. This took us some time to figure out. Then you have to take certain data, because this will be in terms of integral of xs. We're going to try to solve the first two equation. We're going to get some unknown integral in terms of this xs. So when you put them back here, it's a complicated equation. You have to take certain derivatives, and what you arrive at is something very simple. Why is this equation important? Relevant? This is the same equation that you have got if you had a BTZ black hole, if you had a probe Nambu-Goto string in a BTZ of mass m, and you solve the Nambu-Goto equation perturbatively in this way. This is the same equation satisfies. Yes, thanks. Okay, so and this correspondence exists for every order in perturbation. I mean, you'll see this in odd orders because Nambu-Goto equation is odd in this thing. So at every odd order, say 1, 3, 5, you'll see this 1-to-1 correspondence. This equation and this equation are exactly the same. What are the solutions? So if you impose Dirichlet, because we told you that we are going to impose Dirichlet on XS, this is required to compare actually between Nambu-Goto and this. And by the way, I should also mention this is also true in flat space. In flat space, instead of imposing a Dirichlet, we'll solve an initial value problem. And you still see that this correspondence between these gravitational gluing equations and this Nambu-Goto equation persists. Okay, maybe in d-theta we don't know. So what are the solutions? The solution when you impose Dirichlet at the conformal boundary and ingoing at the horizon, then these are given in terms of this superposition of these quasi-normal modes with these quantized frequencies. This Q are some legendary polynomial of second kind. And for illustration, I'll just choose the lowest energy mode. So XS1 is given by this. And in second order of solving the equation, you also get tau A2 and sigma A2. This A0 also contributes to them. What happens when you go to the boundary? You see that now this reparametrization modes, which are the dynamical modes of the interface, this now knows the information about this Nambu-Goto solution that you have for the junction in the bulk. This is a perturbative construction. So if you have a non-perturbative result, there are possibilities that this reparametrization dynamics of the interface can somehow give you information about the what Nambu-Goto solution you have for the junction in the bulk. Okay, so this is what we call a glimpse of the answer. So to summarize, as I told you, so the solutions of these junction conditions essentially have these three parts: the Nambu-Goto part, the correction due to lambda, and this rigid deformation parameter, correction due to this. You can impose a Dirichlet boundary condition and an X, that's both on XA and XS, that will kill this alpha k gamma k, but will not impose Dirichlet on T and R. That gives you this Nambu-Goto solution. Oh, by the way, I should show this. That if you impose a Dirichlet on tau A, that also kills this thing, which we don't want, A0, which is the Nambu-Goto solution. It does not allow. So we have to relax Dirichlet on T and R, so that you see this Nambu-Goto solution as well as this deformation, this rigid deformations. And so what we have constructed perturbatively up to 8th order in perturbation, I'm not showing you very high order results, that we have this solutions are dual to ICFT with a dynamical interface where there is, just less than 1 minute. So it's dual to an interface CFT2 with dynamical interface where the dynamics is of time reparametrization modes. These time reparametrization modes can encode the solutions of Nambu-Goto dynamics. And this correspondence persists at nonlinear orders. For example, I'm showing you XS3. So it has this is like the back reaction of this Nambu-Goto, the first order Nambu-Goto part. And this is exactly the solution of a probe string, a cubic fluctuation of a probe Nambu-Goto string in a BTZ background is exactly the same. This is the Nambu-Goto part, this is the tensile part, this is, for example, the rigid part, and these are the cross terms, and this pattern keeps repeating higher and higher order in perturbation theory. So what are the outlook? Is a non-perturbative proof. For this, we need to solve a very non-trivial problem of generalizing Chesler-Yappe numerical holography in presence of a junction. That's part one. Part two is that, so this analogy is true at classical level. If we are able to quantize our ADS3 gravity in the Chern-Simons language, can we see aspects of first string spectrum? This is my last slide. Aspects of string spectrum from this setup. So it's gravity plus junction. Can that give you part of string spectrum in ADS3? How can we generalize this to higher dimensions? For this, we have to add more degrees of freedom on the brane. Otherwise, the degrees of freedom counting will not work. And the last part is that, so previously in this interface, we had this tensile string. Lambda was the string tension was the only parameter, and that people know how it appears in the boundary observables. Now we have some additional parameters. Are they physical? Do they appear in, for example, if you compute the transmission coefficients of this across the interface and entanglement in this dynamical eye safety 2 thing? That's the future goal. So this, yeah.
Does anyone want to ask one question? Yes.
Aware that the string is the string worksheet is one-dimensional, but is your construction related to the ADS BCFT construction where you have a brain in the bulk with an angle? Is it related to this construction by any from?
I'm not able to listen to it. What's the question?
Can you speak closer to the mic?
Can you hear me now?
Yeah.
Okay. Is your construction related to higher dimensional brains in the ADS bulk?
That's what I said. I mean, you can do this, but I'm not sure if that problem is solvable unless you add further degrees of freedom on the brain. Just a tensile brain will not work because of the degrees of freedom counting. But probably it's possible. You add scalar field on the brain and then maybe it's possible.
Okay. Thank you.